Hi, so what we've got here is a large battery. It's a zinc bromine battery, and you can see it's charging at the moment, so the bromine's at the bottom here, collecting very nicely. We've got a clear bit of electrolyte, and hiding in here is the zinc. Now we're going to break this down and show exactly how this should be made. The reason I'm doing this video actually is a friend of mine, Clarence.mentor, is giving this a go. He's making a whole bank of these things. And I thought I would do this as an example so that it would help, really, to see how I actually built it. Now it's based on US patent 312802, which Clarence sent me because that's what he was going to base his design on. So I've based that on that patent if you want to look that patent up. Now Clarence actually has set up a webzine, a web magazine called ownpower. And his idea is to gather that information together and distribute that information out. And I'm obviously really in support of that because I'm all about sharing information. And if you want to contact Clarence to get a copy of his magazine, then it is, I've got it written here, ownpower, as one word, at act.zn.org, or you can write to him, which is Clarence.mentor @gmail.com, and I'm quite sure he'll be more than happy to send you a copy of ownpower. I did write to check that I could actually give that information out, and he was pretty good with that. Okay, let's break this down. As I say, this is a zinc bromide battery, just missing its electrolyte. So what is it? Well, it's got a pretty top on it, or at least I think it's a pretty top, and that top's got a hole in it because we need to stick an electrode through there. It's just a circle of plastic with another bit of plastic wrapped around it, and that forms a top. The key thing actually is this bit here. Now Clarence sent me a patent number 312802, which is actually pretty much what this is built around. So it's built around that patent. If you get that patent and have a look, you'll see pretty much the same thing. And it uses a container of a porous clay. Now I did look for a container of a porous clay. Couldn't find one. Thought about making one, because as you know I'm a bit of a potter. Then I thought, that's not going to be easy for people to do. So then I had to rethink about it. So this began its life as a fire brick. So I cut a fire brick in half, carved it round into a circle, cut out a depth with a hole cutting saw to make the pot, and then left some little lips on it so that it rests on the top there and doesn't drop to the bottom. So it forms a kind of cup in the centre of the battery. Now that's where the zinc is going to go. So we'll put the zinc in there. Because it's porous, of course, the electrolyte will seep through and actually attack the zinc. And because it's aluminosilicate, it's going to be it's going to be inert in that atmosphere as we charge that battery. So that's why I made the choices I did. And now you'll see that the top actually is kind of a blue colour. And that's because I rubberized the top. Because what's going to happen is that's going to soak up the electrolyte and get wet. Anything on here is going to come into contact with the electrolyte. So I dipped it in this material, Plasti-Dip. Plasti-Dip actually is a plastic coating material normally used for tool handles. You can dip or paint it. I dipped it on until I got a nice rubber coat along the top, so the electrolyte can't soak into the lid that I've made. It wouldn't really matter, the lid's plastic, but it can't do it. The next component we've got here is the positive electrode, because the zinc becomes a negative electrode, remember. Now we have made this before on previous videos. What it is a bit of aluminium foil encased in some conductive high density polyethylene. That's this section here. Then there's a couple of bits of graphite foil glued onto that. It's glued on with heat, incidentally. And then there's some non-conductive high density polyethylene finally put around there. So we made the electrode from scratch. And as I say, we've done videos on how to make those electrodes. If you want to know exactly how to make that, just review one of those videos. Now the container itself I actually thought was awesome. It is in fact a candle holder from my local supermarket. So all you're supposed to do really is drop a tea light in there and you get a pretty candle holder. So I got this candle holder because it's a nice volume, it's 1.5 litres. It has this little sort of section in here which is kind of cool, and a wooden base for it to sit on. So the whole battery goes together like that. Candle holder, then our positive electrode which we've made, then our pot from the fire brick which we've made, and then we put in the zinc, and on goes the top, and that will be the battery. Obviously we're going to put electrolyte in there in a minute, and later I'll talk about the electrolyte. Now this pot, because it's a pot, will take lots of different kinds of zinc. We could put zinc powder in there, we could put zinc granules in there, we can use scrap zinc, which is what I'm going to use because I've got some scrap zinc foil. crush it up a little bit, poke it in there. As long as those zinc pieces are in contact with each other, it's going to be a really nice negative electrode. So if you're using powder or granules, you need to keep it compact to make sure that they actually touch each other. Now this battery, the energy is stored in the electrolyte. It's not stored on the electrodes. So when you think about other batteries, things like a lithium-ion battery and things like a manganese dioxide battery, the energy actually comes from the electrode material itself, the active material on the electrode. These are very unusual in that they come from the electrolyte, and that makes them sort of really good for flow batteries. So it's kind of like a stationary flow battery, if you like. Now, zinc bromide batteries are really well known. There is a lot of information about zinc bromide batteries. So if you want to know more about them, just have a read up on them. There's just such a lot out there. This is a specific build for a well-known chemistry, and it's meant to help people build their own devices. So what we're going to do really is scrunch up the zinc, pop it in there, leave a tail out here, and fill that with electrolyte. Okay, so what we've got here is 1.5 litres of 2.5 molar zinc bromide. That's going to go in here. Now, the key to understanding this battery is that realisation that the energy isn't stored in the battery plates. They don't really matter, actually. They're just at a point at which we can transfer the energy. The energy is actually going to be stored in here and the separation of this. Now, 2.5 molar means there's a specific number of atoms, molecules, floating around in there. When we charge it, what we do is we transfer 2 electrons per molecule, because it's ZnBr2, so zinc has +2, 2 Br minuses, we've got 2 electrons per molecule. Now a mole is a specific number of molecules. It's roughly 6 times 10 to the 23 molecules. It's a lot of molecules, and we have 2.5 times that. Actually, this is in fact 2.5 molar zinc bromide with 0.5 molar sodium bromide to help with conductivity. Because as we charge this, what we're doing is we're pulling out the zinc and depositing it as zinc metal, and we're pulling out the bromine and depositing it as bromine liquid. So it will go down in conductivity as it charges. So as it gets near to the end of its charge, the conductivity is going to drop, and so it's going to be kind of self-limiting because it can't pass any more charge. That is a cool thing if you want that, but it can be a bit irritating, so 0.5 molar of sodium bromide will help to continue that charge. Now then, when we're charging, we are passing a specific number of electrons, 2, for each molecule of zinc bromide that we separate out. So we separate the zinc and deposit it, we separate the bromine and deposit, and that takes 2 electrons. If we have 1 mole of electrons, then we've got 6 times 10 to the 23. Here, obviously, we've got 2.5 moles, so it's 6 times 10 to the 23 times 2.5, or if you like, 18 times 10 to the 23 molecules. That will take 2 electrons each, so we need 36 times 10 to the 23 electrons to make sure that that is totally separated. And that's because that's the amount of zinc bromide we've actually physically got here as a big lump, and we need that number of electrons. Now, luckily enough, coulombs is the number of electrons. If we pass 6 times 10 to the 18 coulombs across a wire, what we have in fact got is an ampere second. An amp hour is 3,600 coulombs. An amp second is 1 coulomb per second passing a point, and a coulomb is a specific number of electrons, 6 times 10 to the 18. So you can work out how many electrons you need, and therefore how many amp hours that battery is going to give you from the amount of zinc bromide you've got, because that's where all the energy is stored. Now I understand that's a bit, quite a bit of math actually, but it's relatively simple. Just look up ampere, look up coulomb, and then you're going to be there. And if you look up Avogadro's number, you'll know what the moles mean. So it's actually pretty simple stuff. So when we pass that in there, we will separate that out to the amount of coulombs or the amount of amps, and we will reverse that. Now obviously it's not 100% efficient, there's going to be lots of inefficiencies because it's a diffusion process. That is, everything separates. When we turn it off, it begins to diffuse across again, and diffusion is slow, takes energy, and is inefficient. So you're going to expect roughly an 80% return of that energy. Something round about there will give you a ballpark figure of what it is that your device is going to store. So you can calculate for the volume of material, the molarity of the material, how much energy you're going to store in the battery you build just by using that information. Now I mentioned it was a diffusion process, and that makes it slow. So although a lot of energy is going to be stored in here, it can't be released in microseconds. That's the job of supercapacitors. It is a battery, so in those terms it'll be a little slower, so it'll be energy dense. But the ability to release energy quickly is power density. So power density is energy over time. So although there'll be a lot of energy in here, it won't have a high power density. It's not going to crackle wires, anything like that anytime soon, because it's relatively slow. So you need to be aware of that. Now, the power density, the ability for that reaction to happen, is to do with the surface area of the electrodes and the diffusion rate across the electrolyte. So if you have a small surface area electrode, you're going to get still same energy density, but the power density will be rubbish. If you have a higher surface area electrode, you'll get much better power density. So the power density of this, my bit of zinc that I put in there, is going to be quite low. If I did powder, compact it and put electrodes in, it would be much higher. If I did something to villate the surface, so it's a bigger surface area, it would be much higher, and so on. This actually is really easy to make, and there's always a trade-off there, because a viliated surface actually can be terribly difficult to make and can be quite expensive. So if you want to accept that trade-off of having lower power density but higher, but it's reasonable energy density and a lower cost, then that's the way to go. But it'll be up to you about what it is that you want to do. Okay, I'm going to fill this with the electrolyte now, and then we'll get the thing on charge. Okay, that's it, ready to go. I've filled it with electrolyte, connected it to the power supply, and it's ready to charge. Now, the eagle-eyed will have noticed a couple of things about the positive plate. One, it's not at the bottom. Remember I talked about that little indentation and quite liking that, and how the fact that the plate's not actually at the bottom. And two, it's full of holes. Now, I've done that because according to the patent, the bromine should settle at the bottom, and this allows it to do that. My experience is a bit of diffusion. The bromine will settle to the bottom, but there's still a bit of diffusion, and the holes allow it to do all of that stuff. The charging regime actually is not like other batteries. You don't put it at a specific voltage. What you do is put it at a specific current density. It needs to be somewhere between 20 and 50 milliamps per square centimetre of electrode surface. So if you've got 100 square centimetres, you're going to charge this at 2 amps. You need to turn the voltage up so that 2 amps will pass. That's a lot of voltage. Now if you're doing it too high, you will see the water splitting and it'll be bubbling. So turn your voltage down and reduce your ampage. That's how you charge these things. Now this thing, remember, it is a bromine-based battery, and bromine's a halogen. So if you smell something like a pool, then you're getting bromine coming off. You'll be able to smell that typical pool smell. The bromine actually stays captured. You don't want to spill it. If you spilled this when it's in its charged state, you're essentially spilling bromine everywhere. Now, I'm not a great one for scare stories, obviously. I mean, I think you should give things a go. But you also have to do it with a measure of caution sometimes. And halogen batteries are those things that you need a measure of caution about. So make sure that you read up those caution measures. Because remember, this is an extremely popular battery. And there's a lot of information about it and how to deal with it. Don't just look at this and think, yeah, I'm going to give that a go. Do read up about it a little bit, particularly on the safety measures of it, because it is a halogen battery, and particularly on the charge and discharge characteristics of it. I'm just giving you a quick introduction on how to go about this. This is by no means in depth of everything about this battery. You can make this battery from this video, you can charge and discharge this battery from this video, but I can't urge you enough to do a bit more reading before you go ahead, just to make sure you know what you're doing. Anyway, this is ready to charge, so just turn it on. Now I've got that set at a very low voltage, so if I bang up the voltage, and I'm going to charge it around a couple of amps or so. So I've got 9 volts on that and now it's charging. You should be able to see there's a kind of a yellowish colour forming already on the plate, which is the collection of the bromine. So here it is charging, and you should be able to see the bromine forming on that positive plate and sinking to the bottom. Okay, because it's a video, I've only been charging it for about 5 minutes, and you should notice quite a few things. All the bromine sinking to the bottom, this bit's nice and clear. I've actually got a little motor here that I'm going to attach. That has considerable power in it already, actually. So I just wanted to demonstrate that it is in fact working. It'll take a while for that to charge, actually. Now you'll know it's charged because the ampage will drop down a bit, and you'll need to put the voltage up to maintain the amp rate, because remember it's charged by current density. As we look at this, we can see there's no off-gassing. So it's, even though it's going to be it is actually charging at the moment at 7.6 volts, we're not splitting the water because it's preferentially plating the zinc and gathering the bromine. Once it's done that, what it's going to do is start splitting the water. So you'll be able to see the gas being given off, and that gas will be hydrogen gas. Now it is giving off a tiny amount of hydrogen gas because they all do. All these reactions happen at voltage plateaus and they're all in competition. So it's a very small amount, but it's really tiny. But you do need to pay attention to the bromine gas possibility and the hydrogen gas possibility. So it's just like a lead acid battery. When you charge a sulfuric acid battery, it gives off hydrogen gas. When you have a lot of sulfuric acid batteries and you're charging those in a big bank of them, then you don't do it in an unvented space. And you've got the same thing here. This can't be charged in a completely sealed area because you're just creating problems. Just like if you tried to charge a lead acid battery in a completely sealed area, one battery doesn't really matter. 100 batteries, you're going to have a problem. So you don't charge batteries in sealed areas, you make sure that you vent them. The other thing that we could do with this, if the liquid does bother you, me it doesn't bother because, I know all about these things, I know how to take care of them, so I really don't care. But if it did bother you, then you could gel the liquid with something like fumed silica. Fumed silica is silicon dioxide. It's actually got in this brick as well. This is an aluminium oxide silicon dioxide brick. If you put a lot of fumed silica in there, it'll go very gel-like. Once it's very gelatinous, of course, you're not going to spill it. I mean, a little bit of liquid spilled makes a big mess. When you gel it, you won't make that big mess. So you could also gel the thing. That would certainly help. But that is how to make a big battery. Now the discharge voltage is 1.8 volts, so you're going to need a few of them to get to 12 volts, but if you want to make a big battery, there's a really good way of making a huge battery. Now I thought I'd share that with you and the information about Clarence and what he's up to. I hope you enjoyed the video. I'll go on and finish charging this and see what it can do, and thank you very much for watching.